Our goal here is to look at the general problem-solving strategy to figure out the period of oscillations, and sometimes you'll hear it be called the period for small oscillations. So, but I'm going to try and talk about oscillations in general. Let's go ahead and get into it and look at it. Okay, so first thing that you want to do is determine a differential equation. How do you do that? That's usually sum of forces equals ma, or sum of torques equals I alpha. Remember, that gives you the differential equation because acceleration is d squared x dt squared, or x double dot. And sum of torques equals I alpha. Alpha is theta double dot, or d squared theta dt squared. So we get our differential equation. Essentially, that just means write down your force equation or your torque equation. Then think, do you need or can you use the small angle approximation, which essentially means is theta less than 10 degrees? Or do you need it? Not for torsional. For torsional pendulums, I don't know if you realize this, but we didn't need the small angle approximation. We never used it for that one. So, but if you're dealing with the pendulum, obviously, if you're dealing with a horizontal mass spring or a vertical mass spring, there's no angle at all. But if you have a pendulum, if it's a simple or a physical pendulum, you might need to check, is our angle always going to be under 10 degrees? If you go up to 20, that's still fairly decent. I think somewhere around 40 degrees, the percent errors start to get large. Anyways, after you write your differential equation and determine if you can use the small angle approximation, or if you even need it, then you need to get a differential, get your differential equation in this form, either negative something x equals x double dot. And again, this is just d squared x dt squared, or negative something theta equals theta double dot, which is d squared theta dt squared. Is that still on the screen? Just barely. Okay. So basically, that gets your differential equation in this form. And so once you do that, next step, omega naught is the angular frequency of oscillations, is the square root of that something. Or if it's an angular problem, it's the square root of that something. All right. Finally, you can get the period using this equation. Solve it for the period and you've got it. And now, just so I can see something here, let's go ahead and look at an example and see how this works out. We want to go to board 2, I think. And I want to do this. So this is equation 15.21 in workbook volume 3, which is on page 15. In volume 3. Whoops. So if you need to see the solution, I'll give a link to that somewhere after in the comments or something. But so here's the idea. We have a rod that's got some length L. At 3/4 of that length from the ceiling, we're going to attach a spring constant, a spring that has constant K. So the givens in this problem, we know the length, the mass of the rod, and the spring constant. And then my claim is, or the question is, how would I get the period of small oscillations? And the key word here is small. Okay, so let's try and walk through this and see what we can do with this. And is this, all right. So step 1 is write the differential equation. And I think that's actually part A of this problem. So if you want to try and do this yourself, you can hit pause. I'm going to start going in 3, 2, 1. Here we go. I would use torque for this problem. I see that this pendulum is going to be swinging. It's a physical pendulum. This does not seem like a good candidate for forces. I'm going to have to figure out the torque caused by this spring, which is going to be a little bit tricky because I'll have to use that spring force. But I'm going to start with this equation. The sum of torques equals I, and I'm just going to say theta double dot, where theta double dot means the same thing as alpha It means two derivatives of theta. And now I'm going to say, in this case, this is the positive k hat direction for torque, right? My thumb point, I guess if I write this is x and this is y, k hat would be z direction, excuse me, is out of the page. So positive torques are this way, negative torques are this way. So I'm going to slap a k hat on that. All right. So now it might help if I draw this thing at a slight angle. So what I'm going to do is I'm going to redraw this thing at a slight angle to help me understand the torques. When I draw this at a slight angle, I hope that was about the right length. I can see that the spring is going to have to stretch a little bit. And you might say, is this going to angle? Yeah, it will, but if we keep things small, a small angle, if theta is small, then this is going to be approximately horizontal. All right, and we saw this spring is going to stretch some distance here. That distance, let me see what notation I want to use to match this. I think I'm just going to call this x. So we'll just say x is the amount it gets stretched, not delta x. So if you're wondering what I was wondering about, right, you could say that this was, whatever. I'm going to call the amount of stretch x, okay? And let's see, what else do we know? We got 3/4 L. All right, so what forces are going to cause torques? If you want to pause the video and guess, go for it. So you might, or what forces act on this thing? And then we'll do the torque equation after that. So 3, 2, 1, here I go. There could be a force this way at the pivot point, Rx. There could be a force up here, Ry. Let me make sure that's showing up. Focus is getting kind of janky. There we go. There's going to be a force right here. I'll call that force subscript S for the spring. Okay, is that legible? Barely. And then we also have a force at the center mg. And so we can see now it's not just as simple as the examples I get shown. We have to do a little bit of work to figure out this side. Okay, so there's going to be a torque caused by mg, and there's going to be a torque caused by the spring. And then these forces cause no torque. Why? Line of action through pivot. Line of action through pivot. No torque. So all this is equal to I theta double dot in the k hat. All right, let's get the torque due to mg. So in this case, this distance is, I believe, L/2. This force is mg. And then what was the angle? I think this angle was theta. So this angle is theta. So the torque due to mg should be L/2 mg sine of theta. And it's in the negative direction. So it's in the negative k hat. Now I've got to get the torque due to that spring. This one's a lot trickier. I know that well, let's go ahead and draw it here. Whoops. I'm trying to label this picture a little better. So we had 3/4 L is the distance from the pivot to where the spring force is applied. This is the spring force, which has magnitude Kx. And then let's get the angle right. I think this angle is theta. So this angle in here is 90 degrees minus theta. So the torque for that one should be, oh my gosh, this is going to be a little bit crazy. It's going to be the distance, which was 3/4 L. It's going to be the force, which is Kx, the amount it was stretched. And then there's going to be an angle, which is sine of 90 degrees minus theta. And that direction is, it's also trying to go opposite the positive k hat direction as far as torques go. It's trying to twist it this way. So that should be a negative k hat. And all this equals I will get out of the way. Give me a second. Okay. So we're trying to get the differential equation. We're almost there. Well, we basically got it. Now we just need to clean it up. This is the gravitational torque. This is the spring torque. And this is I theta. That's sloppy. Theta double dot. Now I'm going to clean this up, canceling what I can here. K hat drops out. Whoops. Then a different color. But notice both of these terms have a negative sign on it. Furthermore, this is cosine of 90 degrees. And you might be thinking, oh man, we're in trouble here. Let's keep going. L over 2 mg sine theta plus 3/4 L kx. Whoops. It's not cosine 90. It's cosine theta. Jeez. Sorry about that. Dumb. Equals I theta double dot. So I got rid of my k hats and I cleaned this up a little bit. Now what I want to do is think. We want the period of small oscillations. That's the key word that says assume theta is less than 10 degrees. Sine theta equals tangent theta equals theta, and cosine theta is essentially equal to 1, unless you're doing an energy problem, which we're not going to be doing that, right? So you could say it's 1 minus theta squared over 2, but for our torque problems, just assume cosine theta is essentially equal to 1, right? The next term in the Taylor series is so small, it's negligible. All right, good enough. So now we're looking at this. I'm going to rewrite this over here. Oh my gosh. I can take this angle and make it theta, and I could take this angle and make it 1. I'm kind of confused here. We have a problem. Let me show you what I mean. Let's go back to our general strategy. I want to make this differential equation in the form of negative something times x equals x double dot, or negative something times theta equals theta double dot. Now look at what we have. Come on, go back. I've got something that's mixed here. I've got a theta and a theta double dot, but here I have an x. It sure seems like everything here would work hunky-dory if I could just get this x written in terms of theta somehow. If you want to try and figure that out on your own, pause the video. I'm going to explain it in 3, 2, 1. Okay, here we go. I've got a triangle here that looks like this. This side was, I believe, 3/4 L, and this was theta, and this is x. Now you might be saying, wait a minute, this distance is 3/4 L. Keep in mind that for a small angle, this side was essentially the same as the hypotenuse. So either way you want to do it. You could have called this side 3/4 L because they're approximately equal if theta is small. So now in this case, I see that sine of theta is equal to X over, and this is the right angle here, 3/4 L. But if we're using the small angle approximation, sine theta equals theta. So notice that X is essentially equal to 3/4 L theta. And I'm going to pause and make sure I didn't flip this. Let's see, bringing this up. Okay. So notice this is units of meters, meters times radians. The units match up. So this is looking pretty good. If you take this result and punch that into here, you will then have a differential equation in the right form. So I've got the solution up on my screen. The rest of this is algebra. There's not a lot of complicated physics. So if you want to pause the video here, that's great. If you want to finish this out and then check the solutions, I'll provide a link to the solutions. I'm going to go ahead and do a quick screen share with the solutions so you could see the final results if you want. So again, pause the video if you don't want to see the answer worked out. All right, let's do share screen 1. Let's make this, okay, so let's move this here. All right, so here's kind of the picture that I was trying to draw earlier. I think somewhere right about here is the line we got to using the small angle approximation. That's where I got to there. And then at this point, you could use this moment of inertia up here. And then hopefully eventually you get to this type of differential equation, rearranging that. I found that is omega naught. So it's some weird thing. This is omega naught. You could write it maybe in different forms. And from there, you can get the period. Finally, if you care, if you look at the end of the rod, we could say the X maximum, right? The maximum distance the end of the rod moves will be given by these parameters. The velocity of the end of the rod would be given by, take a derivative and an omega naught pops out. You could kind of think of this as V equals R omega, right? Where I believe these two pieces here end up being omega. And the units check out. So that's how the oscillation angular frequency relates to the amplitude of velocity oscillations. Okay, so I think that's enough. You could follow along with there. That's pretty good. Let's stop this video. I'll put a link to this